Download this code from codegive.com, link in the description below. 16 Cache System Design Fundamentals with Code Examples, Python. This tutorial dives deep into the fundamental principles behind cache system design, covering 16 key aspects that are crucial for building efficient and scalable caching solutions. We'll illustrate each concept with Python code examples using the functools library for memoization and basic dictionary-based caches. While these examples are simplified, they highlight the core ideas. For production-level caching, consider using dedicated caching libraries like redis-py, memcache, or cachetools. 1. Cache purpose and goals. Why cache? Before designing a cache, define its purpose. Caches aim to reduce latency, serve frequently accessed data faster than retrieving it from the original source, example database, API. Improve throughput, handle more requests without overloading the origin. Reduce cost, lower costs associated with database queries or API calls. Improve availability, provide data even when the original source is temporarily unavailable. The goals should be quantifiable. For example, reduce average API response time by 50% or offload 70% of reads from the database. 2. Cache types, identifying the right fit. Different cache types suit different scenarios. In-memory cache fastest, but limited by available RAM. Suitable for frequently accessed, relatively small data sets. Example, functools.ru_cache. Disk cache slower than in-memory, but can store larger data sets. Useful for persistent caching across restarts. Example, serialization/deserialization to a file. Distributed cache scalable across multiple servers. Ideal for high-traffic applications and data that needs to be shared across multiple processes or machines, example redis, memcache. Content Delivery Network, CDN caches static content, images, CSS, JavaScript, closer to users geographically. Choosing the right cache type depends on factors like data size, access patterns, performance requirements, and infrastructure. 3. Cache placement, where to cache. Where you place the cache significantly impacts performance and complexity. Client-side caching, caching in the user's browser or mobile app reduces network requests for static content. Edge caching, caching content closer to users at edge servers, example CDN. Improves latency and reduces load on the origin. Proxy caching, caching at a reverse proxy server, example Nginx, Varnish. Offloads requests from the application servers. Application level caching, caching within the application code. Simplest to implement but may not scale as well. Database caching, caching at the database layer, example query results, frequently accessed rows. Multiple layers of caching are common for optimal performance. 4. Cache invalidation, maintaining data consistency. Cache invalidation ensures that the cache contains up-to-date data. Common strategies include time to live, TTL. Each entry has an expiration time. Simple, but may serve stale data. Event-based invalidation. Cache entries are invalidated when the underlying data changes. More complex, but ensures data consistency. Example listening for database update events. Write-through. Data is written to both the cache and the origin simultaneously. High consistency but increased write latency. Write-back, write behind data is written to the cache first, and then asynchronously written to the origin. Faster write performance but a risk of data loss if the cache fails. Code example, TTL. 5. Cache eviction policies, making room for new data. When the cache is full, an eviction policy determines which entries to remove. Common policies include least recently used, LRU evicts the least recently accessed entry. Often the best general purpose policy. Least frequently used, LFU evicts the least frequently accessed entry. First in first out, FIFO evicts the oldest entry. Random replacement evicts a random entry. Time aware, TTL based evicts entries that are closest to their TTL expiration. Code example, LRU using functools.ru_cache. 6. Cache consistency models, balancing performance and accuracy. Strong consistency cache always reflects the latest data. High accuracy, but can impact performance. Write-through caching. Eventual consistency cache may temporarily contain stale data, but eventually converges to the latest data. Higher performance, but eventual staleness. TTL-based caching, write-back caching. Choose the consistency model that balances the need for data accuracy with performance requirements. For example, user profile data might tolerate eventual consistency, while financial transactions require strong consistency. 7. Cache key design, uniquely identifying data. A well-designed cache key is crucial for efficient cache lookups. Consider these factors. Uniqueness the key must uniquely identify the data being cached. Simplicity keep keys as short as possible to minimize memory usage. Information rich include enough information to retrieve the correct data. For example, instead of just using a user ID as the key, you might include a timestamp if the data is versioned. Concatenate multiple fields if necessary to create a unique key. Use a consistent naming convention for keys. Code example, key design. 8. Cache stampede, dogpiling, prevention, avoiding overloads. A cache stampede occurs when many requests simultaneously try to access the same expired cache entry, overwhelming the origin. Strategies to prevent it. Probabilistic early expiration, cache jitter add a small random value to the TTL of each entry. This spreads out expiration times and reduces the likelihood of a stampede. Locking, mutex when an entry expires, acquire a lock before refreshing it. Only one process can refresh the cache at a time. Stale while revalidate serve the stale data from the cache while asynchronously refreshing it in the background. This improves responsiveness. Code example, cache jitter. 9. Cache partitioning and sharding, scaling the cache. For large caches, partitioning, splitting the cache into smaller segments, and sharding, distributing segments across multiple servers, improve scalability. Consistent hashing a widely used sharding technique that minimizes key remapping when nodes are added or removed. Key range partitioning assign keys to shards based on a range of values. Hash-based partitioning hash the key and use the hash value to determine the shard. 10. Cache monitoring and metrics, measuring performance. Monitor key cache metrics to understand performance and identify potential problems. Hit rate the percentage of requests served from the cache. A higher hit rate indicates better cache effectiveness. Miss rate the percentage of requests that miss the cache. Asterisk latency asterisk the time it takes to retrieve data from the cache. Asterisk cache size asterisk the amount of memory or disk space used by the cache. Asterisk eviction count asterisk the number of entries evicted from the cache. Use tools like Prometheus, Grafana, or cloud provider monitoring services to track these metrics. Set up alerts to detect anomalies or performance degradation. 11. Cache compression, reducing storage and bandwidth. Compressing cache entries can reduce storage requirements and improve network transfer speeds. Use compression algorithms like zip, standard, or bit.ly. Consider the trade-off between compression ratio and CPU overhead. Code example, simple compression. 12. Security considerations, protecting cached data. Asterisk encryption asterisk encrypt sensitive data stored in the cache. Consider encryption at rest, when stored, and in transit, when transferred over the network. Asterisk access control asterisk restrict access to the cache based on roles and permissions. Asterisk data masking asterisk mask sensitive data fields to protect user privacy. Asterisk vulnerability scanning asterisk regularly scan the caching infrastructure for security vulnerabilities. 13. Cache API design, a clear interface for interaction. Design a clear and consistent API for interacting with the cache. Asterisk get, key retrieves data from the cache. Asterisk set, key, value stores data in the cache. Asterisk delete, key removes data from the cache. Asterisk clear, clears the entire cache, use with caution. Asterisk increment, key, amount atomically increments a numeric value, useful for counters. Asterisk decrement, key, amount atomically decrements a numeric value. Use consistent naming conventions and provide clear documentation for the API. 14. Cache warm-up, populating the cache initially. Cache warm-up involves pre-populating the cache with frequently accessed data. This avoids a cold cache and improves initial performance. Asterisk load data on startup asterisk load data from the database or other sources when the application starts. Asterisk seed the cache with synthetic requests asterisk simulate user requests to populate the cache. Asterisk background refresh asterisk periodically refresh the cache with the latest data. 15. Testing and validation, ensuring cache correctness. Thoroughly test the cache to ensure its correctness and performance. Asterisk unit tests asterisk test individual cache components. Asterisk integration tests asterisk test the cache in conjunction with other parts of the system. Asterisk performance tests asterisk measure cache performance under different load conditions. Asterisk consistency tests asterisk verify that the cache data is consistent with the origin data. Asterisk invalidation tests asterisk verify that cache invalidation mechanisms are working correctly. 16. Fallback mechanisms, handling cache failures. Implement fallback mechanisms to handle cache failures gracefully. If the cache is unavailable, fall back to the origin, database, API. Use circuit breakers to prevent cascading failures. Implement retry logic to handle transient errors. Code example, fallback mechanism. Conclusion asterisk. Effective cache system design is crucial for building high-performance, scalable, and reliable applications. By understanding and applying these 16 fundamental principles, you can create caching solutions that meet the specific needs of your system. Remember to carefully consider factors like data size, access patterns, consistency requirements, and performance goals when making design decisions. And always remember to monitor and tune your cache to ensure optimal performance. The Python examples provide a starting point. Consider using dedicated caching libraries for real-world applications. Okay, let's dive into the fascinating world of cache system design. This will be a comprehensive tutorial covering 16 fundamental concepts, complemented with code examples, mostly in Python for clarity and conciseness, but I'll highlight where other languages might be preferable. We'll cover everything from basic concepts to more advanced considerations. Table of Contents *. 1. Introduction to Caching *. Cache. 2. Cache hits and misses * Understanding performance. 3. Cache placement policies * Where to store data. 4. Cache replacement policies * Evicting the right data. 5. Cache coherence * Maintaining data integrity, multi-core / distributed. 6. Cache consistency * Balancing latency and accuracy. 7. Write policies * How and when to update the main store. 8. Cache size * The Goldilocks problem. 9. Cache topology * Organization and structure. 10. Cache invalidation * Keeping data fresh. 11. Concurrency and thread safety * Handling multiple requests. 12. Cache key design * Efficient data retrieval. 13. Cache expiration * TTL, time to live. 14. Cache monitoring and metrics * Tracking performance. 15. Distributed caching * Scaling beyond a single machine. 16. Cache aside, lazy loading, a common pattern. 1. Introduction to caching. Why cache? The fundamental principle behind caching is to store frequently accessed data in a fast, easily accessible location, the cache, to reduce the latency and cost of retrieving it from a slower, more expensive source, the main store. Latency reduction * Caching drastically reduces the time it takes to retrieve data, improving responsiveness. Imagine fetching data from memory, cache, versus a hard drive or network call, main store. Throughput improvement * By serving requests from the cache, the main store experiences less load, allowing it to handle more requests overall. Cost reduction * If the main store is a database or API with usage-based pricing, caching reduces the number of requests, potentially saving money. Availability improvement * In some cases, a cache can continue to serve data even if the main store is temporarily unavailable. 2. Cache hits and misses, understanding performance. Cache hit * When the requested data is found in the cache, it's called a cache hit. This is the desired outcome, as it provides fast retrieval. Cache miss * When the requested data is not found in the cache, it's called a cache miss. The system must then retrieve the data from the main store, potentially updating the cache for future requests. The hit rate, number of cache hits / total number of requests, is a crucial metric for evaluating cache performance. A higher hit rate indicates better performance. The miss rate, number of cache misses / total number of requests, is the inverse. 3. Cache placement policies, where to store data. This refers to the algorithm used to determine where in the cache a particular piece of data will be stored. Common placement policies include direct mapped cache * Each main memory location maps to a specific location in the cache. Simple but prone to collisions, multiple main memory locations mapping to the same cache line. Fully associative cache * Any main memory location can be stored in any location in the cache. Provides the best flexibility but is more complex and expensive to implement, requires searching the entire cache. Set associative cache * A compromise between direct mapped and fully associative. The cache is divided into sets, and each main memory location maps to a specific set. Within the set, the data can be stored in any location. N-way set associative means each set has n slots. Code example, simplified direct mapped cache. 4. Cache replacement policies, evicting the right data. When the cache is full, a replacement policy is needed to determine which data to evict to make room for new data. Common replacement policies include *least recently used, LRU evicts the data that has been least recently accessed. Generally performs well but can be complex to implement precisely. *first in, first out, FIFO evicts the data that has been in the cache for the longest time. Simple to implement but may not be optimal. *least frequently used, LFU evicts the data that has been accessed the least frequently. Can be effective for identifying infrequently used data. *random replacement evicts a randomly chosen piece of data. Simple to implement but often not the best choice. Code example, LRU cache. 5. Cache coherence, maintaining data integrity, multi-core/distributed. In multi-core processors or distributed systems where multiple caches might hold copies of the same data, cache coherence ensures that all caches have a consistent view of the data. This is crucial to prevent stale data from being used. *snooping protocols *caches monitor, snoop on, the bus/network for write operations from other caches. If a cache detects a write to a shared data block, it either invalidates its own copy or updates it. Common in shared memory multiprocessors, SMPs. *directory-based protocols *A central directory maintains information about which caches have copies of each data block. When a write occurs, the directory sends invalidation or update messages to the relevant caches. Scales better than snooping for larger systems. Note * cache coherence is a complex topic typically handled at the hardware level, in multi-core processors, or through specialized protocols in distributed caching systems, discussed later. Implementing it from scratch is often not feasible or necessary in application-level caching. 6. Cache consistency, balancing latency and accuracy. While cache coherence ensures that caches have the same data eventually, consistency addresses how long it takes for changes in the main store to be reflected in the cache. There are two primary approaches. *strong consistency guarantees that all reads after a write will return the new value. This is the most straightforward but also the most expensive in terms of latency and complexity, requires immediate synchronization. Eventual consistency guarantees that all reads will eventually return the new value. Allows for higher availability and scalability but sacrifices immediate consistency. Common in distributed systems like databases and cloud storage. Eventually can range from milliseconds to seconds, depending on the system. The choice between strong and eventual consistency depends on the application's requirements. For financial transactions, strong consistency is usually essential. For social media feeds, eventual consistency might be acceptable. 7. Write policies, how and when to update the main store. Write policies determine how and when data written to the cache is also written to the main store. *write through every write to the cache is immediately written to the main store. Simple to implement and provides good data durability but can introduce latency. *write back, write behind writes are only made to the cache. The main store is updated later, typically when the cache line is evicted. Reduces write latency but requires more complex cache management, dirty bits, and increases the risk of data loss if the cache fails before the main store is updated. *write around writes go directly to the main store, bypassing the cache. Useful for data that is unlikely to be read again soon. Can help prevent cache pollution, filling the cache with infrequently used data. Code example, write-through cache, simplified. 8. Cache size, the Goldilocks problem. Choosing the right cache size is a balance. Asterisk small cache asterisk high miss rate, negating the benefits of caching. Low memory footprint. Asterisk large cache asterisk lower miss rate, but higher memory consumption and potentially increased latency for cache lookups, especially in fully associative caches. The optimal cache size depends on the application's workload and the cost of memory. Profiling and experimentation are essential. It's often better to start small and increase the size as needed based on observed performance. 9. Cache topology, organization and structure. Cache topology refers to how multiple caches are organized, particularly in distributed systems. Asterisk centralized cache asterisk a single cache server that all clients access. Simple to implement but can become a bottleneck. Asterisk distributed cache asterisk data is partitioned across multiple cache servers. Improves scalability and availability. Common partitioning strategies include asterisk consistent hashing asterisk distributes data across servers based on a hash function. When a server is added or removed, only a small amount of data needs to be rehashed. Asterisk rendezvous hashing asterisk each client independently selects the best server for a particular object by computing a weight for each server and choosing the one with the highest weight. 10. Cache invalidation, keeping data fresh. Cache invalidation removes stale data from the cache to ensure that clients receive up-to-date information. Different invalidation strategies exist. Asterisk time-based invalidation, TTL data is automatically invalidated after a certain time period, time to live. Simple but may not be accurate if the underlying data changes more frequently. Asterisk event-based invalidation asterisk the cache is notified when the underlying data changes. Provides more accurate invalidation but requires a mechanism for the main store to notify the cache, example message queue, webhooks. Asterisk manual invalidation asterisk an administrator manually invalidates data in the cache. Useful for specific situations but not scalable for frequent updates. 11. Concurrency and thread safety, handling multiple requests. When multiple threads or processes access the cache simultaneously, it's crucial to ensure thread safety to prevent data corruption and race conditions. Techniques include asterisk locks asterisk using mutexes or semaphores to protect critical sections of code that access the cache. Asterisk atomic operations asterisk using atomic operations to perform read modify write operations on the cache without locking. Asterisk concurrent data structures asterisk using data structures designed for concurrency, such as concurrent dictionaries or queues. Example, thread-safe cache with locks. 12. Cache key design, efficient data retrieval. The choice of cache key is crucial for efficient data retrieval. Keys should be asterisk unique asterisk identify each piece of data unambiguously. Asterisk compact asterisk avoid unnecessarily long keys, as they consume more memory. Asterisk consistent asterisk generate the same key for the same data every time. Asterisk contextual asterisk include relevant information that might affect the data, example user ID, timestamp. Good key examples. Asterisk user 123, for user data with ID 123. Asterisk product 456 inventory, for product 450 SIXS inventory. Asterisk API underscore response slash users, page equals 1, for caching API responses. 13. Cache expiration, TTL, time to live. TTL is a common mechanism for automatically invalidating data in the cache. Asterisk absolute TTL asterisk data is invalidated after a fixed amount of time. Asterisk sliding TTL asterisk the TTL is reset each time the data is accessed. Keeps frequently used data in the cache longer. Choose a TTL that balances the need for fresh data with the desire to reduce load on the main store. Too short equals too many cache misses, too long equals stale data. 14. Cache monitoring and metrics, tracking performance. Monitoring cache performance is essential for identifying bottlenecks and optimizing the cache. Key metrics include hit rate/miss rate measure the effectiveness of the cache. Cache size utilization monitor how much of the cache is being used. Eviction count track how often data is being evicted from the cache. Latency measure the time it takes to retrieve data from the cache. Error rate identify any errors or exceptions related to the cache. Tools like Prometheus, Grafana, and cloud provider monitoring services can be used to collect and visualize these metrics. 15. Distributed caching, scaling beyond a single machine. When a single cache server can't handle the load, a distributed cache is necessary. Common technologies include MEMC8 a distributed memory object caching system. Simple, fast, and widely used. Redis an in-memory data structure store that can be used as a cache, message broker, and database. More feature-rich than MEMC8. Hazelcast an in-memory data grid that provides distributed caching, data partitioning, and other features. Cloud-based caching services Amazon Elasticsearch, Google Cloud Memory Store, Azure Cache for Redis. Managed services that simplify deployment and management. Distributed caching introduces challenges related to data consistency, fault tolerance, and network latency. Careful consideration of these factors is essential. 16. Cache-aside, lazy loading a common pattern. Cache-aside is a widely used caching pattern. The application logic is responsible for interacting with both the cache and the main store. One read when the application needs data, it first checks the cache. If the data is found, cache hit, it returns the data from the cache. If the data is not found, cache miss, it retrieves the data from the main store, stores it in the cache, and then returns the data to the application. To write when the application needs to update data, it first updates the main store and then either invalidates the corresponding entry in the cache or updates the cache directly. Code example, cache-aside. Summary and next steps. This tutorial covered 16 essential cache system design fundamentals. However, real-world cache systems are often more complex and require careful consideration of specific application requirements. Profiling and experimentation always profile your application's performance and experiment with different cache configurations to find the optimal settings. Understand your workload the characteristics of your workload, read/write ratio, data access patterns, will significantly influence the best caching strategy. Choose the right tools select the appropriate caching technologies and libraries based on your needs. Consider trade-offs caching involves trade-offs between latency, consistency, cost, and complexity. Remember that caching is not a silver bullet. It is a powerful tool that can significantly improve performance, but it requires careful planning and implementation. Good luck.